Okay, we're going to try to do GES 2 here, March 2026, most recent paper as to date. Usually these March papers are quite difficult for the GES 2, but as we just changed from SQA into QS, we should see if there's any differences. All the rules are the same, everything else looks the same on the surface, so no difference there. What about the actual questions themselves? So let's have a quick skim through the paper, see how it is. It's really weird, but I do expect to see some repetition in some of these questions, like repetition of topics. They seem to do that quite often these days on the GS2, which I think is kind of a waste of a question, right? But whatever. If you know it, you know it. Stainless steel vessel. Define or determine the final equilibrium temperature. That's actually quite a difficult one, unless you got the little custom formula for it, which I'm not going to teach you, I'm afraid. We're going to use the slightly longer method, but it gets us there. Just this final equilibrium involves a bit more algebra, really. Just a little bit tougher to get there, but we can get there. Okay, so it's quite a tough question to start with. A gas is at a high pressure in a cylinder. Initial gas, perfect gas, blah, blah, blah. These would be pervert equations and QMACTs, right? So gas equations, no problem. State what's meant by entropy of fusion and ice. Oh, the classic ice question. You're heating up some ice. So there's also going to be a QMACT question, isn't it? This one actually has QMACT in there as well. That's a bit strange. I don't know if you need that guy. We'll have to see if we even use that. That's a bit of a red herring. And then here we've also got a QMACT up here, haven't we? Specific heat capacity. Specific heat capacity of stainless steel. Specific heat of water. They just shortened it to, and then here they just put C. And then here we've got specific heat capacity of water written in full. It's not consistent. Specific heat capacity of water. Yeah, that many kilojoules per kilogram Kelvin. That's just right. Here we got it again. Specific heat of water, not heat capacity. Whatever. Synonyms. Okay, so all kind of very, very similar kind of topics. Okay. Then we've got the big one, right? The big engine one. This is normally the last thing we study on the course. Yeah, quite a difficult problem. Normally we can actually skip this on the course. It depends on how much time you've got at the end. We're going to go through it all today. Again, they've kind of really chewed up the units down here. Those kilonewtons per meter squared per millimeter is a bit of a pain. And they do something else in here. Yeah, the indicator cards. They have this little of a rarer version of the indicator cards. Kind of like the harder version of this question. But again, we'll go through it. That'll be fine. Heptane there. At least they're not doing anything too crazy with the heptane. Just stoichiometric mass of air and the mass of carbon dioxide. And they've given us that air is 23% oxygen by mass, which is, we need to know that. They don't give us the rest of the information that we need to know, so it's a bit strange to get a bit of information on it. But quite a straightforward question, at least, not a dual fuel. One time we had like butane and propane mix or something like that, and we had to do a bit more work on it. And describe the principles of a vapor compression refrigeration system, basic aircon or refrigeration question. I'm not going to go through the details of that one because you know it already probably from other courses. Okay, electrical circuits, usually quite difficult. It's actually quite a hard question. It's like a backward style question because it's find the resistance, right? And usually we are given the resistance and we calculate everything else, but it won't be too bad actually. We tackle this one quite early on before you get into the usual run of things. But we'll go through that question as well, of course, right? This one has made a comeback. Oh my goodness, haven't seen this one for a while. I stopped teaching this in the course because I just haven't seen it so many times for so long. And here we have it. So we'll go through it again today. Make sure we can make it make sense. It's a really crummy question, like iron wire. I mean, I'm gonna Google that quickly and see if I can find some actual iron wire. My guys were saying, like, why would you use iron? Wouldn't it be very high resistance and wouldn't it be like brittle? Like, how would you be able to bend the wire in the first place? Like, wouldn't it have to be iron is not steel, so kind of brittle, I suppose. I'll have a look at that. It might not be. If it's pure steel, if it's pure iron, it would be soft, right? That's so strange. I have to look into it. But a bit of a MacGyvered question, I think. And that's why it's disappeared in the recent exams. It just came back again. So we'll have a look at it. Electric fire, oh, that classic electric fire or heater, as I'd like to call it. And they brought about the electric fire wording on it in the most recent exam papers. They changed it to heater instead of electric fire, but the old classic question bank questions have fire still in there. So that's an easy one to do as well. And then this flux density, magnetic flux, FBIL sine theta, usual stuff, nice and easy. Bit of naval arc towards the end. Then this is a really easy one as well. They even give you the formula, which they took away for a bit and they put it back in again. I kept thinking they're going to take this formula away from us, and eventually they did last year, 2025, for a couple of questions, I think, a couple of exam questions, and now they've had this change from SQA to QS. Maybe they've changed examiners or changed writers and they just didn't know about it, brought it back again. It's kind of little things like that to tell me what's going on. Okay, but a very easy question, very easy question. Determine thrust load, coffin and bulkhead, very simple question as well. Naval architecture, not the hard naval architecture questions, not the harder versions. All right, so let's start on number one. Okay, so let's do number one. I think I made some space down here. Where is he? There he is. So this is a tough one to start with, a bit of work on it. A stainless steel water vessel has a mass of 3 kilograms and contains 12 kilograms of water at this temperature. Stainless steel water vessel made from stainless steel but is for water. Oh my goodness. Why would you call it a stainless steel water vessel, not just a stainless steel vessel? Has a mass of 3 kg, has that much water in it, and you're going to add some more water into it. So let's sketch out a diagram about what they're even talking about. Because as usual, it's difficult to say things correctly or difficult to say things clearly. We've got a stainless steel vessel that's full of cold water, and we're going to be putting hot water into it. So here's my hot water pouring in there. Might as well call it hot water, and this one cold water, just so we can see what's going on. I say cold, it's really 22 room temperature, and we're adding in 70 degrees. And then we've got the stainless steel, the steel vessel around the outside. Determine the final equilibrium temperature. Now there is a really short one-time formula for this. I don't tend to use it because this question is just like a harder, I would say a rarer question, and therefore we don't need to train on it so much. Anything with final equilibrium temperature is just going to be a bit tougher. I'm going to be trying to use the same method as I always use, which is to build it into a big table, a big rickety table. So let's start off with the name of the objects. We're going to have a cold water and the steel. Oh yeah, I forgot to say that the heat lost should equal the heat gained. This is actually what we're modeling everything around. So the heat lost in the system must equal all the heat gained in the system, which means that we could say this a little bit better. We could say we're going to use a Q mach T. So Q is energy, heat energy, yeah, okay, good. Energy, just checking I got that right. And this will be from the hot water, because that's going to be losing it, and that will be equal to the energy gained, the heat energy gained by the cold water, and also the stainless steel, the steel shell, right, the steel container. And this is a little bit strange because technically we're losing energy here, we're gaining energy here, so technically this will be a negative and this will be a positive, but we're not going to worry about that. We don't have to in physics, we can just make it work. We will make it work by using mathematics. We can actually put a negative in here, and I'm going to incorporate a negative into my system. Oh no, I've just thought of a way to make this maybe a little bit better, but we'll keep it simple before I start changing things up. Let's just keep it the same way we always did it, and it'll work, right? So Q of the cold water, this would be Q, or let's just call it cold water, sorry. This would be cold water. We also got the steel shell, the steel container, and then we got the hot water. Okay, and just so we're clear about this, that cold water is going to be gaining. It's going to be a gain. The steel is also going to be gaining. It's going to get hotter, and the hot water is going to be lost. It's going to be losing because the heat lost should equal to heat gained in the system, right? So all these guys have to equal each other out. I'm just doubling down on my explaining things so I can spot any mistakes I make along the way. Okay, we're going to make this big rickety table. It's not the best, but it'll do. And we're going to start this off with the initial conditions, the final conditions, the delta T, which is really important in this case, and then the Q mach T, QMC delta T. Like I said, I'm keeping it this way because this is how I've done all my notes so far, and I think I might have developed a slightly cleaner method for this, but whatever, this will do, this will work. Okay, so the reason why this is not so good is because that initial column I'm going to use is not like the best. So initial is going to be Q mach T, so we talk about MCT, MCT, and MCT. All right. So the reason why this is not so good is because the mass doesn't actually change. The initial is just going to be the same for the mass. Do we know the mass of that cold water to start with? Yep, we're starting off with 12 kilograms of water. 12 kg. I can also see I've got the mass of the steel there, so we put that in as well, 3 kg. Do we know the heat capacities of the water? They should be down here. Heat capacity of the water is 4180 joules per kilogram Kelvin. Oh, too many G's in that. There we go. Squeeze it all in because it's good if we can get the units in there as well. Extra brownie points. Okay, do we know the temperature of the starting temperature? Yeah, we do. It was, what, 22 degrees. There we go. A heat capacity of the steel, I think, is given, yeah, 500 joules. So it's 500 joules per kilogram Kelvin. 500 joules per kilogram Kelvin. And the initial temperature was 22 degrees C. The mass of the water being added into it is another 15 kilograms. So 15 kg is being added in. Heat capacity will be the same as the other water because it's still fresh water, kilograms per Kelvin. Okay, and then the the initial temperature of that starts at 70 degrees. There we go, 70 degrees C. That's all our data to start with. And then we are trying to calculate the final temperature. So I'm going to call this X. And the final temperature will be the same for all of them because we will reach an equilibrium condition after we put that hot water in with the cold water. The container as well, the stainless steel container, will all reach the same temperature at the end of the day after we let it run for a bit. So delta T. This is where the tricky bit comes in with this final equilibrium temperature. These are just the harder ones. So the delta T. So what I do here is I say, what about if we imagine the final temperature? The final temperature is going to be somewhere between 22 and 70. So let's just say, I don't know, it was 50 or something. Then what you do to keep this delta T positive is you do the big number minus a small number. So that's going to be X minus 22. Right? Because we don't actually know what the final temperature is. I shouldn't put this 50 in here. That was just an example. Let me get rid of this. It's just so I can get my head straight when I actually do the calculation. This will be delta T. It has to stay positive. The reason why it's staying positive is because of this situation over here. We're just saying they're all positive. So even if we're losing, we're still going to keep it as positive. It's quite common to keep delta T as being a positive number. Okay, right, so we're going to do the same thing here with the steel. This is going to be delta T. The final temperature will be higher than the initial, so it'll be the same setup. Again, I'm imagining this will be 50. 50 minus 22 will go as a positive number, so it'll be X minus 22 over here. Okay, and you know why this is important, because when we do the last one, the hot water one, this is going to be loss, right? And it's going to be the other way around. Let's say the final temperature was 50, then to keep this thing positive, you do 70 minus the 50. So we're going to do the final temperature minus the initial. No, I meant the initial minus the final. This is actually backwards to the rest of it over here. Quite complicated, quite an annoying setup. That's why it's a difficult one to do. It's just a little bit fiddly on this bit here. Okay, now we should be able to put everything together over here, and again my table is a bit skewed, so we're using this, and we're using this guy in our final Q Mac T. That's the M, that's the C, and that's the delta T. A bit skewed, I know, I could make it a little bit better. I say that every single time, and then we just use it as is. So this is Q, and this will be the cold water, and the mass there will be 12 kilograms times by the heat capacity, which is this guy, times by delta T, which will be X minus 22. Let me just zoom in a bit so we can see that a little bit clearer, because I think we can just pull everything out of the table now. There we go, that's a Q Mac T. We're going to do the same thing for that steel. I call it S. I could call it steel, couldn't I? I could call it stainless steel. Okay, so 3 and then 500 and then X minus 22. And then over here we can have Q of the hot water. And this will be the mass times by the 4180 times by this 70 minus X. Okay, originally we said that the heat gained is equal to heat lost, or vice versa. So I should be able to drop all these in their respective places, right? This is cold water, is going to go right there. This will be the steel, that'll be added onto it over here. And then the hot water will be this one over here. And this is why this question's a pain, because look at all this algebra we got to solve. It's not that bad, you know, it depends on your algebra skills. A lot of the guys find the algebra difficult, so this is a bit of a nightmare. Let's simplify what we can. We're going to get some really big numbers on this, but it is what it is. We can't really make it much better. So we're going to do 15 times by 4180. 62,700, 62,700. Okay, that's still times by 70 minus X Might as well times it by 70 while we're at it. So times this by 70. I'm going to move my calculator off screen just so I can see what I'm doing. I'm multiplying these two numbers together. We got 4389000 minus 62700x. Big numbers, and there's not much we can do about it. Okay, that's the left-hand side done. Let's just scoot that across, and let's start doing the next one. We're going to do 12 times by the 4180 on my calculator. So 12 times by 4180. 50160, 50160, and this will be x minus 22. Multiply this in, that would give us 50160x minus, and then this will be 22 times by that number. Let's get it up. Times by 22. Whoa, big numbers. 11. So it would be minus 1103,520. And then we're going to do this last one over here, which will be 3 times by 500. That will be 1500. And then x times by x minus 22. So we're going to multiply this in. Oh, there should be a plus sign, not an equal sign. So 1500x and then 1500 times by 22. Let's just check I did that first bit right. 3 times by 500 is 1500 times by 22. 1500. 33,000. All right. Okay. So lots of big numbers. Now we want all our x's to be positive, and everything else, all the x's to be positive and all collected together on one side. So this guy and this guy can be added together, and I'm also going to add this one over. I'm going to move this one over here by adding it, so it's going to get added in. So I'm going to add together all those x numbers there. So we've got quite a few of them. So it'll be the 62700. That's going to come over and be positive because I'm going to add it to both sides, plus the 160 plus the 1500. We get 114360. 114360x. Huge numbers, right? Fiddly. And then what's going to happen is we're going to do the same thing with all the other numbers. We're going to get all these, like these just regular numbers by themselves. We're going to add them to the other side. So these are all negatives. They're actually going to become positives when they go over to the other side, and they're going to get added into this 4 million. We're going to add in all these two other numbers over here. I'm doing so much rearranging all at once. It's just saved me the hassle of actually writing it all out. So, but as long as you can see what's going on, it's okay. And these are hard questions, right? They're just really tough. So 11,03520, probably correct, and then plus the 33,000. All right, add all that together. 55255. 5525520 is equal to, quite repetitive there. Yep, 5525520. Okay, cool. And we should just divide this by this 114360 guy, and we should get our answer. And the answer will be our final equilibrium temperature. So let's try. I think the final equilibrium temperature should be between the two initials, right? It should be somewhere between the 22 and the 70 that we started off with. So let's see what happens. We are dumping in to this quite a lot of hot water. It's 15 kilograms, right? So 15 kilograms is being put into 12 kilograms. So that'll be it'll be like about halfway between them. It'll be a little bit hotter maybe. The heating up the stainless steel doesn't take as much energy. So halfway between 22 and 70, I don't know, what about 50 or something like that. Let's see what we get. Fingers crossed. Oh yeah, it might come out to be exactly 50. Look at that. 55 divided by 11 over 50. So this number divided by 114360 comes out to be 48.316. 48.137. No, 31. It's too early in the morning. 317 degrees Celsius, and this is equal to X, which is also the final temperature of everything, final equilibrium temperature. And like I said, my guess was about that, or my estimate based upon it. So determine the final equilibrium temperature of the vessel in the water. This will be it. That will be the final temperature. Okay, very good. That's number one. Let's do number two. Probably need to look a little bit more space on this guy. Alright. Number two. A gas is contained at high pressure in a cylinder. When it's vented to atmosphere through a nozzle, explain what happens to the temperature of the gas released. Yeah, that's a question, but there's no points on it. Are they talking about it here? Or is that what the question's about? Because okay, when it's entered the atmosphere, a perfect gas. Is that a question? At a perfect gas, the initial temperature and pressure of this much is cooled at constant pressure until its temperature is 10 degrees. So this is a question, but it doesn't have any marks attached to it, and it's not part A. I mean, I could write a sentence. Maybe I'll get some marks for it. Question 2. A gas is contained at high pressure in a cylinder. When it's vented to atmosphere through a nozzle, explain what happens to the temperature the gas is released. So this is like a special case. I mean, you're venting through a nozzle. Explain what happens to the temperature the gas is released. I think it's like a counterintuitive one. You got a high pressure gas inside of a cylinder, and it's at a certain temperature and it's vented to atmosphere, so it will occupy a larger space. I guess this is going to be a pervert, a PVMRT, or P1V1T1 is equal to P2V2T2. Yeah, I guess you could explain it by using this. The pressure. It might be quite. I think you just got to know it. It's just a definition question. So I can't remember because it's a new question that we haven't seen before, and I should know it. 1 second, I'll just go look it up. Yes, okay, so I had to look it up. I did it previously, and I had to research it a little bit because, again, we haven't seen this kind of question before, even if it's a question or not. So haven't seen this kind of question before, so I didn't know the answer off the top of my head. The gas expands quickly. This is an adiabatic expansion process. Well, I meant to know about those, and I should look into it a bit more because there's a couple of different expansions, and I think it's adiabatic and non-adiabatic. So heat is not transferred to the environment because it happens really quickly, because the expansion happens super quickly. Like all the heat energy stays inside the gas. It doesn't have time to transfer to the environment. The temperature of the gas that escapes will decrease as the gas expands. The number of vibrations per cubic volume will decrease. Yeah, so technically the temperature is decreasing. What's happening is the energy inside the gas is maintained because it's not lost to the environment. It's just basically saying if you expand a gas, what happens to it. So the volume will increase, the pressure will decrease, and what does the temperature do? Well, apparently the temperature will decrease. That seems really counterintuitive. If the volume increases but the pressure decreases, can I get it to? Can I give it some numbers? And actually see that happening, because it's a non. How do you say it? It's directly proportional. It's a non-directly proportional. No, it's an inversely proportional relationship. Oh my goodness. Number of vibrations, you literally, it's just a definition question. Adiabatic expansion. If you look it up, you'll see that it just says this, right? It's just the definition of it. I reckon if I just Google it, I'll be able to see that. Can I do that? Just Google it real quick. See if it comes up with that. Just so I'm not just making stuff up. When a gas released from a high pressure to the atmosphere through a nozzle, its temperature typically decreases. The phenomenon is primarily explained by two concepts. Whoa, the Joule-Thomson effect. Whoa, that's cool. I don't know anything about this. Adiabatic expansion. A gas exit, it pushes against the surrounding atmosphere to carve out a space. PV work, the surroundings, temperature drop. You see, it's really complicated. We don't go to these definition questions so much on the course. It's not even labeled up as a question anyway. So I just wonder if I can actually get some numbers on it. But again, it's a new style of question, one I haven't seen before. That's why I'm stumbling over it so much. Let's see if we can work it out. I wonder if I can actually give it some numbers. I shouldn't, because I've just been making stuff up. It depends on how much it expands. They say the temperature decreases. The reason for that is that you have a certain number of gas molecules inside of the gas when it's at a high pressure and a low volume. And as it increases, the number of gas molecules will stay the same in there. So we're going to have like, this will be high volume, no, low volume, high pressure. This is high volume, low pressure. And you measure temperature by the number of like molecules like hitting into the side. Oh, that's pressure. Number of molecules vibrating. And apparently they vibrate less. There's less vibration here because there's more space between them. Strange. Okay, I shouldn't have done all that on a video, should I? See, I'm not 100% clear on it. But I'm not going to lose any marks if I get it wrong, because it's not even a mark question. So let's do the calculation ones underneath. And we'll worry about those later, I suppose. I would actually say it's like a definition question. It looks like I don't know if it should even be in the course because it's not here. We haven't had any adiabatic expansion process questions before, directly like that. Like they're always calculation questions. One more thing I want to say about this paper, actually, just too, is that usually there's some really big definition questions on here. And the only definition question on here is this describes the working principles of vapor compression for 10 marks. Usually there can be up to 4 questions like that where you go to definitions. I suppose this counts as a 1, but it's not marked, so strange. All right, so back to work then. Part 2A, a perfect gas has initial pressure to temperature of all this stuff, yes. 3.75 bar, this many degrees C, that means 8 liters. It's cooled at a constant pressure. Well, it's not the same as this introduction question. It's just a completely different setup. It's at high pressure in a cylinder where it's vented to atmosphere. Explain what happens. Maybe they're talking about that's the high pressure, and instead of venting it to get atmosphere, they just they cool it, which could be the case. Perfect gas. So we got perfect equations PV MRT, and then we've also got P1 V1 T1 and P2 V2 T2. These are kind of like my setups for the question. Just get myself organized. I haven't done this paper for quite some time, so I'm a little bit rusty, I think. So this is to bring it all back. So P1 V1 T1. I'm actually going to start with this one no matter what we do because we need this in data anyway. I think the first bit is going to be, it says a perfect gas's initial pressure and it's cooled, respectively, at constant pressure. So it will be a P1 V1 T1 question anyway. Again, they have thrown in this C as well, which is a part of a QMAC T. This is a heat capacity, specific heat capacity, which we don't need for this question. So why is it here? Nobody knows. I don't know. Again, it's not normal to have extra information. So let's get to work. P1 V1 T1, and then P2 V2 T2. Probably everything's in its mixed up units. The usual units that we need will be in there somewhere, but some of them will, some of them won't, and we got to convert them all. So a perfect gas is 3.75 bar. This is 375,000 pascals, right? You times by 100,000 pascals, 100,000 to get from bar into pascals. That's 3.75 atmospheres. Okay, and this is the same as newtons per meter squared, as we saw in GES 1 the other day. The volume 1 is given as 280 liters, which is 0.28 cubic meters, and the temperature is given as 145 degrees Celsius, and we're going to add 273 to get into Kelvin. So let's do that straight away so I don't forget about it. 418. So 418, oh, I can't write, 418 Kelvin. All right, okay, so far so good. Let's do the other side. Respectively, it's cooled at a constant pressure, so the pressure should be the same. And the temperature now goes down to 10 degrees C. At 273, that'd be 283 Kelvin. And yeah, what's the question here? A perfect gas is initial pressure, temperature, and volume. It's cooled at a constant pressure. How is that a question? It doesn't say anything. What do we have to determine? Obviously, we got to find the volume. The final volume is down here. What is going on with this question, guys? What? So I can work out the final volume? That's what I was gonna do? I can work out the initial mass by using perfect equation? Alright, so this 2 marks is for up here. That would make sense. But then why is it question B? I mean, oh, that should be question A. And this should be question B. There we go, that makes sense. So I do get 2 marks for saying this adiabatic expansion process. So we should call it 2A. Oh my goodness, fixing their typos. So you get 2 marks for like a little definition question. I would actually just skip that because we don't train it on the course. If it comes up again and again and again, we'll look into it, right? We'll study it, but it's a bit too theoretical for what we do. Okay, so where was I? After fixing that, this should be 2B. BI. So we're going to find the initial mass of the gas. We'll do that in a second. I'm going to work on the volume because I've got everything set up in terms of volume. I need to kind of do this anyway. Yeah, I don't know. I could just use this to do the perfect equation to get the mass of the gas. We could do that right now. Let's do that right now. Let's try and keep stuff in order a little bit. So PV is equal to MRT, and we're going to use P1, V1, T1 actually for all this, and we've got everything just ready to go. So P1 is 375. The volume is 0.28. The mass is what we're trying to find, so I'll call it X. The characteristic gas constant of this guy is 290, because I'm using just joules, not kilojoules, and the temperature is 418. Okay, so this is the perfect equation set up, ready to go, and we're finding X, which is going to be the mass. I'm going to multiply these slowly together. So many typos on these questions, and just there's new typos every single time. So this is 10,5,0,0,0. Yep, that's right. Okay, you would have thought the qualification of Scotland would be so much better than Scottish qualifications authorities. Times this other two numbers together. There we go. Okay, one. Oh my goodness, I like the repeating numbers. Only 1, 2, 1, 2, 2, 0. Okay, and we just divide it down on the other side to get our X by himself. This divided by this should equal our answer. 10,5,0,0,0 divided by 1,2,1,2,2,0 equals, and we get 0.866. 0.866 kilograms of gas. 19 kilograms, because that's what the X was. It was the mass of the gas for part BI, I suppose. I've relabeled all this. It's still BI. It's good. Initial mass of the gas. This is the mass of the gas. Right? Difficult to tell because we don't know what kind of gas it is. You could probably tell what kind of gas it is by its characteristic gas constant. And then, but you can't guarantee it, to be honest. And then it's difficult to know because we don't know how much gas weighs, because you don't really work with weights of gases very often, unfortunately. So we don't know for sure. We have to kind of trust the process. Hopefully it's fine. Hopefully it's trustworthy. Okay, and the final volume, well, this is going to be my volume here. I'm going to call that X as well. And we're going to use our P1, V1, T1. So P1, V1, T1 is equal to P2, V2, T2. The pressure's kept constant, so we can ignore it. We can get rid of it. This was in pascals up here. Okay, and then the volume there, we're going to plug in the numbers of 0.28. The temperature is 418. Here the volume is unknown, and 283. And this is the little calculation we're going to do. Oh yeah, the mathematics is so much easier here. On this question, the first one we did was a little bit hard. I'm going to calculate this side and then just multiply by 283. So 0.28 divided by 418 equals, and then times the answer by 283. And we get 1895. 0.1895. 69, so I call it 7. And this is equal to X. What was X again? X was the cubic meters of this, so that would be in cubic meters. And let's just check it actually made sense. I think it does, because we start with a large volume, and we've gone down to a slightly smaller volume. That's 280 liters, right? And we've gone down to 189, 190 liters. So it's reduced in volume, and that's because we have cooled it. Perfect gas is cooled at a constant pressure, yeah. So because we cooled it, it's reduced its volume. It's got smaller. So that would be the same as expanding. Heating a gas would cause it to expand, which would be, what's that? Charles's law, the hot air balloon guy. Yeah, Charles's law. So it would tie into that one, and it would be the opposite of it. It would just be reverse Charles's law. So it makes sense. It works very well. And we don't need the C. It's not part of the question. So strange it's there. You sometimes see that occasionally they leave it in when they rehash an old question. Oh, that's the end of number 2. Okay, let's do the next one. Okay. State what's meant by entropy of fusion. So entropy of fusion is sticking things together, which is freezing, basically. The amount of energy required to freeze something, or need to be removed from it in order to cause it to freeze. We should really say it a little bit better, though. We should say the entropy of fusion is the... okay, let's say it properly then. The enthalpy enthalpy of fusion is the amount of energy required to bring about a phase change, is how we're going to say it, required to bring about a phase or state change from liquid to solid, or vice versa. It's fully reversible, it can go in both directions, and that is what it is. The units for it are going to be joules per kilogram, not Kelvin, because state changes happen at a constant temperature. There's no temperature change, so it's just joules per kilogram. And even the formula for it would be the enthalpy of fusion would be, it's a Q T equation, right? Q is equal to mc delta T, but there's no delta T on it because when you do those state changes, they don't change temperature. They're at constant temperature. You get 0 degree ice to 0 degree liquid water, and that's exactly what we're going to do here anyway. So I could just say, what's this? I could actually expand it out for 2 marks. I think I've already done too much. Enthalpy of fusion will be the mass in kg multiplied by the latent heat capacity. Or is the enthalpy of fusion. This will be specific because it's per kilogram. Specific heat capacity. Enthalpy of fusion. Oh, no, that's correct. The amount of energy required. I don't know. I shouldn't say this because I might mess it up. This would be like energy required. Energy required. The mass and the latent heat capacity. That is the enthalpy of fusion. And it's done in joules per kilogram. Latent heat capacity. So maybe we shouldn't call it that. Maybe we should call it enthalpy of fusion. It's the same thing. I'll put it in other words here. This is. You can call it, they call it so many different things. Enthalpy of fusion. That's strange, because isn't it specific enthalpy of fusion because it's per kilogram? Not sure. No. Joules per kilogram. Yeah, enthalpy of fusion. Isn't that specific enthalpy? Anyway. Like I said, too much. I should just stick to the single sentence will get you 1 mark, really, or maybe the 2 marks. You don't really need all this other stuff. I was just putting a little bit extra on, and maybe I shouldn't have kept it simple. Okay, that was part A. Okay, part B is we got this ice, right? And this ice is going to start off very cold ice. It's going to be heated, and then it's going to turn into water, I suppose. And it says it got 250 grams of ice at -20. It's heated to with this many 120,000 joules of energy. Determine what is the final state and temperature of the resultant. Yes, the resultant. Resultant what? Resultant substance? Resultant? Just the resultant. Okay, so we're going to start off with ice, and this is going to be cold ice. It's going to be at -20 degree ice. Yeah, and we're going to heat the ice up until it gets to melting point, which will be at 0 degree C. Then we're going to melt the ice into water, which is also going to be at 0 degree C. And we're going to heat the water up into hot water, and that would be at some unknown degrees Celsius. That's what we're going to calculate. Calculate the final state and temperature. All right, and we are focusing on the in-between stages between all of these. So there's actually 3 different stages. There'll be stage 1, stage 2, stage 3. We can call them such. And the first one, we're heating a solid to a solid. We could write down that this will be, I guess, a solid to a solid. This will be latent. Is it latent? No, it's specific, my bad. This will be specific, which is a Q T equation. Q is equal to mc delta T. Okay, then we're going to switch over in here in the middle. The ice going to water, this is latent, or the specific fusion, right? They call it enthalpy of fusion of water. That's so weird. Specific heat capacity is per kilogram, and enthalpy of fusion is per kilogram as well. I kind of think it should be called a different thing, but I keep chewing up the language. So latent heat capacity, this is just our QMUC, right? There's no delta T because it doesn't change. It goes from 0 to 0. And then we've got specific again at the end. And we're going from 0, this will be a QMUC T again. Muc delta T. Okay, and we're going to focus on these 3 different stages. Okay, we're going to heat the ice up to melting point. We're going to melt the ice, and then we're going to heat up the water. Okay, so phase one, is it all going to be, this is going to be Q muck T, Q M C delta T, and we got a Q, M, C, and T. Okay, we want to know how much energy it's going to take to do this. I know I've got an X over here, I've got another X over here. I'm kind of trying to work out, it's different X's unfortunately. We're trying to work out how much energy is required for this first stage. If we know how much ice we've got, and we do, the mass will always stay the same. We've got 250 grams, so it stays as 0.25 kilograms. The heat capacity of that ice is given here as 2110 joules per kilogram Kelvin. All right, and the initial temperature, or the delta T, sorry, the change in temperature is going from negative 20 up to 0, so it's going to be a plus 20 degree. And we've got enough a piece of information to work out how much energy this requires. So we could call it like Q1 if we wanted to, or just Q. Don't have to call it 1 because in the 1 section, isn't it? It's down here, right? And this will be the MC delta T. So it'll be 0.25 kilograms times by the 2110 times by the 20. And we can calculate exactly how much energy is required for this first stage. Okay, so I'll calculate it. 0.25 times by 2110 times by 20. 10,550. 10,550 joules is how much energy we require just to heat the ice up to a melting point, and it's used 10,000 joules. And in the question they say we got 120,000 to spend. So think of it a bit like a shopping list. We got to buy part one, and we got to buy part two. Whatever's left over from the amount of energy we have, the amount of money we have to spend, the amount of energy we can then spend on part three in order to heat it up to the maximum amount, right? So we've just calculated the cost, the heating cost of that first part to get the ice up to melting point, and that was specific. Now we're going to do the latent, which is going to be part two. This is going to be melting the ice, so it'll be a QMC, Q muck, because again there's no temperature change to phase. We're actually changing the shape of the molecules and how they pack together, going from ice molecules, which is a crystalline structure, into water, which is non-crystalline, and that takes a lot of energy to do it. So we've got Q, let's just change the colors a little bit here, Q, M, C, and we've got nothing else in here. And we're going to calculate how much energy it requires. The mass will stay the same. It'll still be 0.25 kg. The heat capacity, this is latent heat capacity. I'm still calling it C because it still says latent heat capacity, right? They call it entropy of fusion, but there's lots of different names. You can call it entropy of solidification as well. They also call it that as well, just to switch up the names. There's no official naming of this thing. Or a couple of official names, maybe. And this is, you got to be really careful, it's absolutely massive. It's 335,000. So this is 335,000, and we can work out how much energy this takes. So it'll be Q is equal to the mass times by the latent heat capacity, or entropy of fusion. Okay, so 0.25 times by 335,000 gets me 83,750. 83,750. I'm just checking we haven't already gone over the spending limit. Here for Q2, for the melting part, 83,000, 10,000, now we've got 120,000, haven't we? So that's just fine. So now we're going to do part three, and part three, we are actually going to calculate first of all how much energy we have left over, because we just saw for part three, we start off, we're given 120,000 to start with, then we have to minus off the energy down here for Q1, which is the 10,000. And 550, and also minus off this 83, and whatever's left over, this will go towards heating up that water from 0 degrees into like a higher temperature, right? So let's get these numbers then. What do we have at 120,000 minus the 10,550 minus 83,750, 25,700. 25,700 joules. This is how much we have left to spend in order to heat up our water. We're going to do a Q muck T equation, so it's Q is equal to MC delta T, but this time we actually know the Q. I'll keep it all in red, but Q MC delta T. So this time we're going to spend 25,000 heating up that water. The mass of the water stays the same. The heat capacity is given as water, it'd be up here somewhere. Here we go. Specific heat capacity, as we saw in the previous questions, which is very strange because, like I said, they're really testing the same subject a few times, which means they've kind of skipped another subject. Yeah, which is all right as long as you know this one really well. So 41800. I meant 4180 joules per kilogram Kelvin. And the delta T is what we're going to calculate. We're going to calculate how hot this will get. So I could just put it all together. It's really, we don't need that top bit. It's just going to be this bottom bit here. So it's going to be Q is equal to MC delta T. Q is the 25,700. The M is 0.25. The C is 4180, and the heat delta T is going to be this guy over here, right? So we've got everything set up and ready to go. I'll pop it up here, and we're going to multiply these two numbers together and then divide it down underneath, right? And we should be able to solve it. So 0.25, sorry, 0.25 times by 4180, 1045, so 1045x, and it should give us the final temperature of the water. And it's usually about 20-30 degrees. It's not too hot. It's not going to go to boiling. Otherwise, we need more information on the question. Actually, 25700 divided by 1045 gets me 24.6. So I'll just write down what I did because I did it on my calculator. So I'm dividing that by the 1045. Okay. Let's see. 245.593. Yeah, this is degrees Celsius on this one, and that will be final temperature. I know we've got Kelvin along the way, but this will be in Celsius, and you know why that is, because we talk about it all the time in class, right? So no problem. 24. State, determine what is the final state and temperature of the resultant. Well, we've got the temperature, and the final state will be a liquid. Liquid is final state because it could be a solid or it could be a gas as well. That's it. This temperature in degrees Celsius, and it's a liquid. Okay, that was number 3. Let's look at the next one, number 4. Alright, so this is a diesel engine question, and they can be quite difficult because they have a lot of different variations on the question. We can put all sorts of things into this one, right? There's about 8 different formulas technically to go in this, which is why it's hard, right? So 8 formulas is quite a lot to remember for one question. Normally we have 2 formulas per question, so that's why it's a little bit tougher. And there's a lot of variations, but of course, you know, as a diesel engineer, this is a diesel engineer calculation. It's really in the heart of what you want to know, and that's why we've got it here, really. Okay, so we're going to try to calculate this guy. An 8-cylinder, 4-stroke diesel engine has a bore and a stroke. Indicator cards are taken off, and each had a mean effective height of 22 millimeters. This is strange because there's a bit of variation, a modern day variation we've seen quite recently, quite a few times. The new examiner, I would say, really likes this question, likes to do this. The power of the engine was also true to your dynamometer, which gives the steady state torque reading of this much. Calculate brake power. Yeah, so my guy has written down the formulas here. We've got the BP is T2 pi n. Okay. And we just make sure we got all the bits for this one, right? Let's see, T is torque, and it's given as a steady state torque reading of 36,000 Newton meters, so that's just fine. 2 pi is just 2 pi, and N is going to be number of revolutions per second. It is a 4-stroke diesel engine, but it doesn't affect this N, right? You got to be careful about that guy. So, okay, so N is going to be taken from the RPM. We've got 800 revolutions per minute, and what we want is revolutions per second, so we divide it by 60. So 800 divided by 60 gets us down into 13.333. So it's 13.333 revolutions per second. Now if this was we just leave it like this, even if it's a 4-stroke or 2-stroke, it doesn't make any difference. These are all the nuts and bolts. That's all we need. Quite an easy starter question, very nice. So we just multiply all this together, 36,000 times by the 2 pi times by the 13.333. Let's do that on a calculator then. I'll just take my answer here and times it by 2 pi, but you can retype it or just put lots of 3's on it and times it by 6,000. Big numbers. What's that? 30. 159. I put that comma in the wrong place. 15928. 15928, comma, comma. So it's 3 million. Yeah, 0.9. Okay, and this is power, so it'll be done in watts. Okay, so it's 3 million watts or 3 megawatts worth of power. And that's the actual power on the actual engine. That's how much it's actually producing at the time, right? Okay, let's do part B and the current setup with the current fuel and everything. So much it's producing. Indicated power. Yeah, and my guy's written down IP is equal to X plan. X plan, he's got a little different way of writing it. Let's see, X P L A N. If we can get this, right? Because sometimes we don't quite have the information. Let's see, they might give us something else. Yeah, okay, so X plan is nice, but to get the P in there, X is the number of cylinders, which we have as 8. P is the IMEP, is the indicated mean effective pressure. So we're going to step over into IMEP. IMEP is usually the area times by the spring coefficient divided by the length on the indicator cards. And the reason why I say that is because the indicator cards look like a banana, and you want to work out the area, the average area basically, or the average height of this. So you take the whole area and you turn it into a rectangle basically. So if you did area divided by length, you get the height, and that is what IMEP is. The pressure goes up here, and you want the average height of this. It's going to have some very high pressure, low pressure parts of the cycle, and you just want the average pressure, which is what we're doing here. And the reason why I say that is because they chew up the question a little bit. This is where all the details are on this question. Specifically, they say the mean effective height is 22 millimeters, which means if you take of a rectangle, if you take the area and divide it by its length, you do get its height. So this guy is 22. It's 22 millimeters. Okay, 22 millimeters you're going to see is actually fine. I could even put the units in here. I won't put the units because it'll get a bit messy. This phi is our spring coefficient, but they said our spring coefficient is 80 kilonewtons per meter squared per millimeter, which is a right mess. But a kilonewton, kilo is 1,000, so I could write that as 80,000. The newton per meter squared, this is the same as a pascal, so I could write that as pascals. And this will be the same as a 0.8 bar. And this is how you normally get your units actually in the spring coefficient. Normally give it in bar. This looks about right. Normally it's about 1 bar per millimeter, but in this one is 0.8 bar per millimeter. That means for every millimeter you compress the spring in the little testing kit, which I have a picture of it somewhere, just not right on this white, not right here, not with me. Every millimeter you compress the spring, it means you have a pressure of 0.8 bar, which is about right. It's normally about 1. But they give us this really chewed up set of units, and we are looking for the IMEP, which should come out in pascals. So I'll keep it here in 100,000, 80,000 pascals. It's per millimeter, and we're compressing it by 22 millimeters. So we could multiply these units together. It'll be pascals per millimeter. So the actual calculation for the IMEP there would be 22 millimeters times by 80,000 pascals per millimeter. And the millimeters will cancel out because this is dividing and this is multiplying, and we get 22 times by 80,000, and it should come out in pascals, which is just fine for a pressure. Oh, really bad. So the IMEP will be 22 times by 80. Really chewy on that setup. The good news is that they've used this question about 3 or 4 times now. I think 3 times. This is, or maybe 4, in recent years, I'd say. So there's quite a few examples of it, and it's always kind of the same kind of setup. They really don't change it about too much. It looks really hard, but it's really not that bad. 176, and then 4 zeros. That's 1.76 million pascals, because we're talking about pascals, which is 17.6 bar, which is all right. It's a high pressure. But in the bigger engines, this is what we see, and we are talking about a big engine. We've got 3 megawatts on this thing. Sometimes they'll go right up to 9 megawatts or 10 megawatts. Okay, so we got the IMAP, which means we're now ready to do the X-plan calculation. Okay, let's just make sure we got everything else. That is the make sure we got everything else. We should list out all of ingredients here, shouldn't we? Let's bring it across so we got a bit more space. Do I need any more information on it? I think it's okay. That is all the P for IMAP. X we already know. L we know as well. It tells us here we should have the length of the stroke. Yep, it's in there. The area of the stroke. No, but they're giving us the bore. Okay, so we've got some more calculations to do. So how am I going to organize it? Let's make some fresh space. Because we're doing for part B, we're doing IP is equal to X plan. X is a cylinder. P is the number we just got. Is this 176, this guy. That's it, pascals. The L is the effective length. And they tell us the effective length is 400 millimeters. So that's 0.4 meters. Yeah, that's a big engine, is it? Bore is absolutely massive. The bore is going to be the area. Well, we're going to use it to calculate the area. And of course, the bore is the diameter. So what we want to do is take this diameter, turn it into a radius, and turn it into meters, square it, and times it by pi. And that's quite a few stages of working. So I'm going to do it quickly. I'm going to take the bore, I'm going to divide it by 2,000, if you can see that way down here, because the 2 will turn it into a radius. The 1,000 will turn it into meters. So now it's a radius squared, and that's a radius in meters. We square it and times it by pi. This is just my quick way of writing it down so I don't have to do a second calculation, like another side calculation. We do quite a lot of this by the end of the course. So by the time you get through the whole course, you're going to be quite familiar with taking, like, there's my diameter, right? Divide it by 2. That's now my radius in millimeters divided by 1,000. I now get it in the radius in meters, which if I just do this 3500 divided by 2,000, it just does that for me, and square it and times it by pi. Okay, so 0.096 meters squared, but we'll get a few more decimals in that, a few more digits. 2112. 2113 meters squared. I round up the last little bit. That's now the area. Okay, and we need the N, and the N is a little bit different for this one, isn't it? Because it's a four-stroke engine. We get you to take the previous N, this 13.33333, and then divide it by 2, but we'll do the full workings on it. So N is going to be number of revolutions. It's the number of effective strokes per second, and we start off with our revs per minute, which is given in the question. So we're going to take the 800 revs per min. We'll divide it by 60 to get revs per second, which was 13.333. We'll double check that. And we divide by 2 because it's a four-stroke engine, so not every stroke is a power stroke. So we divide it by 2. So 13.333 divided by 2 gets me 6.666. This will be strokes per second, effective strokes. Effective stroke per second. Very nice. Okay. Finally, I think we can multiply this all together in one big calculation. So IP should be 8 times by 1.7 million. This is what I'm saying. It's a very long question to do. Just for a few marks. You do it last. The length of the stroke. The length of the stroke times by the area, the cross-sectional area, will give us the volume of each cylinder. Times it by 8 cylinders, you get the total volume of the engine. And multiply it by the pressure as well as the speed at which it's running. Okay, so let's do that. Let's get that guy. Let's get them all together. Let's see. 8 times by 176, 1, 2, 3, 4. Times, carefully typing in all the digits. Checking as I go. I haven't made any typos yet. Okay. 6.6. The good news is I can double check this answer against the first one we got, because it should be a little bit more than the brake power, right? So we got the brake power as like 3 million, and this is also 3 million, so it should be a little bit more. This indicated power is the theoretical amount of power the engine is producing. So let's write this number down. I got 3612413.5. I might just round off that. Watts. So this is the theoretical amount of power that the engine should be producing based upon its size, right? And the speed at which it's running. 3.6 million, and here we got 3 million, and these two combined will give us the efficiency, and of course the IP will always be greater than the BP. The indicated power will always be greater than the actual power you get from the engine, because you've got mechanical losses in there, and that's the mechanical efficiency for part C. There's a lot of work for just like 8 marks on this. Okay, so for part C, efficiency calculation, efficiency is going to be the brake power divided by indicated power times by 100, depending on which kind of what you're doing in terms of efficiency. This should be the actual divided by theoretical. Sometimes it will be theoretical divided by actual, depending on if you're giving or taking, I suppose. So BP is this 3 million. Oops. IP is the 3.6 million. So what do you think? 90% efficient? Pretty high efficiency. Times by 100. See what we get. A lot of numbers type in. So I like a natural fraction just so it looks easy to see. Double checking. Yeah, looks good. 3612413.6. Cool. They look good. 83%, not 90%. 83.488. 80. Was it 3? 348% efficiency. That's it. Oh, that's a tough one. A lot of work. And all this stuff about the indicated spring constant, you just get so stuck on that you can't even get into it, unfortunately. I mean, who says, like, you know, kilonewtons per meter per millimeter? Ugh, per. So weird. Alright, okay. That was the end of number 4. Let's do the next one. Okay, let's check out number 5. See if it's any better. Okay, number 5. 1.5 kilograms of heptane is completely burnt in air. Determine the stoichiometric amount of air required, mass carbon dioxide in the exhaust gases. So, yeah, okay. So this is a normal combustion question. No, nothing spooky, nothing strange. They're not doing anything really twisted at the end. All right, so let's start off with our basic data that they don't give us, where hydrogen is 1, carbon is 12, oxygen is 16, and air is 23% oxygen by mass, not by volume, as you're used to seeing 21% by volume, 23% by mass. All right, and we are going to start off with carbon. What do I have to do here? It's been a while. Hydrogen, and then total. Let's put these out. Yeah, carbon, we've got 7 carbons, and a carbon weighs 12 each. So we're going to work out the total mass, the relative atomic mass of the carbon in there. So 7 times by 12 gets me 84. 84 parts carbon, effectively. The hydrogen is 16, and hydrogen weighs 1, so 16 parts hydrogen. Oh, those are really nice numbers, because 16 plus 84 gets me a total of 100, which makes checking it a little bit easier, I think. So this is actually the relative atomic mass of the heptane molecule. It actually weighs 100 atomic mass units, which is like the same as 100 protons, for what it's worth. Okay, right, so these are the relative weights of them, and that means we've got 84 out of 100, so 84% of that fuel is pure carbon. Okay, and we've got 1.5 kilograms. So we're going to work out exactly how much carbon we have in 1.5 kilograms of heptane. It will give us the total amount of carbon, and the carbon in that fuel. So 84 divided by 100 times by 1.5. We get 1.26 kilograms of pure carbon in there. We're going to do the same thing for the hydrogen. We'll do 16 out of 100 times by 1.5, and it should be the corresponding amount to make this up to 1.5. I'm doing this to double check I haven't made any mistakes. So 16 divided by 100 times by 1.5 gets me 0.24. So 0.24 kilograms. And you can see that they do add up to be a total of 1.5 kilograms. I'm just using this as a little check, because if you mess this part up here, you have a typo here, everything we do later is going to be wrong. So it's a good little point to check, a little checkpoint to make sure we're on the right kind of track. Okay. Right, so this is what we've got so far. We're all good. We've got this much carbon. So let's get to burning the carbon and burning the hydrogen, because that's our next step, because we are going to completely burn, which means complete combustion, which is good, and we can work everything else we need out after we've done this part. So let's burn the carbon. Okay, and I'm going to burn the hydrogen as well, because we're going to be doing both. Okay, so burning that carbon is we're going to take some carbon, we're going to add in some oxygen, and we're going to make CO2 because we're completely burning the carbon. We're not making carbon monoxide because it says it in the question. It says complete combustion. There's a technical way to say we're making CO2, not just carbon monoxide. So this has to be a balanced equation. So C plus O2 is equal to CO2. All right. Okay. And now we're going to use our little formula, and the formula you need to remember is the mass. No, I got that wrong, haven't I? It's going to be moles. Moles is equal to mass over m. I've only got one formula to remember. I can't remember it. Moles is equal to mass over m. Huh. So, this is actually kilomoles, actually. I just realized. I've been doing this for many years, and I've always been teaching it the same way. It doesn't make any difference to what we do, but actually this should technically be in grams, not kilograms, but never mind. I didn't say anything. Carbon then, how much carbon do we have? We've got 1.26 kilograms of carbon, and we're going to divide it by its atomic mass. Just carbon by itself is just 12. We have up here is 12, so we're going to pop that in. And this will be equal to the amount of oxygen we require to burn that carbon, and it's O2. So one oxygen is 16, but there's two of them, so it's 16 plus 16 to make 32. Okay. The mistake I've made in terms of moles, actually this is perfectly relevant. I didn't say anything. There's no mistakes here. It's all fine. Okay, so of course the calculation we're going to do is going to divide this side with 1.26 divided by 12 and then times that 32 to the other side. It should tell us how many kilograms of oxygen we require. So 1.26 divided by 12 and then times that by the 32, because we're just moving the 32 to the other side, we get 3.36 kilograms is equal to X. So we need this many kilograms of oxygen. So 3.36 kg of oxygen is required to completely burn the carbon. I like to write myself a little note so I understand what I'm doing. There's a lot of stuff going on here. If you annotate your work, write some sentences in English, it'll make things a little bit easier to understand. Right, now we're going to do the same thing, but we're going to burn the hydrogen over there. So hydrogen plus hydrogen plus oxygen is going to make water. These are the products of complete combustion again. So H plus O is equal to H2O. This needs to be balanced, so we need the inputs have to be the same as the outputs. So we need two hydrogens plus one oxygen is equal to H2O. You can see the numbers working there. And we're going to use the same old formula we had earlier. We're going to do number of moles is equal to the mass divided by its relative atomic mass. All right. I shouldn't have put this line in here because it kind of gets in my way. Let's get rid of it. All right. And my question is, how much hydrogen do we have here? How much hydrogen are we burning? Well, we're burning 0.24 grams. 0.24 grams. How much does this comes as a hydrogen 2 molecule, right? So it comes as two hydrogens put together. So 1 and 1 makes 2 because the hydrogen weighs 1. And this should be equal to the amount of oxygen we require. And it's a single oxygen molecule, so it's just going to be 16. Again, these numbers are given up here at the very beginning. And we're going to calculate this guy. So let's go ahead and calculate it. We'll divide the 0.24 by 2. And then we'll times it by the 16. We should get our answer on that. We now got 1.92. So we got 1.92 kilograms, and this is equal to X, we just calculated here. So we need 1.92 kilograms of oxygen is required to burn the hydrogen. Okay, great. So first things first is we worked out how much oxygen we require for all of this. Now let's see what they say in the question. What's the stoichiometric mass of air required? We're looking for the actual air, so we take a few steps now to get us into the air. It's only going to be a couple of steps because it's just stoichiometric amount. There's no added excess air in this, so it's probably like 3 steps. So for part A, we can work out the mass of oxygen. So we look at this oxygen plus this oxygen will give us a total amount of oxygen. This is called stoichiometric amount of oxygen. So stoichiometric is the minimum amount of air or minimum amount of oxygen required to bring about this combustion. In real life, we normally add a bit of extra oxygen in just to ensure complete combustion, but not in this question. Usually in the other questions, yes, they do have it. Okay, so let's add these guys together. So 1.92 is already my calculator, plus the 3.36. 5.28. We need 5.28 kilograms of oxygen for every 1.5 kilograms of fuel that we're burning. And stoichiometric is in relation to the total amount of fuel. It's not per kilogram. That will be called specific. Specific is usually with reference to 1 unit, normally 1 kilogram, or it could be 1 liter or 1 anything, really. 1 cubic meter, 1 liter. But this is not. It is stoichiometric. It's total amount of all the fuel has to be burnt. So we need 5.2 kilograms of oxygen in order to burn all that fuel. This is stoichiometric amount of oxygen. Now we're going to work out stoic air. The stoichiometric amount of air, and air is at 23% oxygen. So we do a reverse percentage calculation for this one. We need some quantity, which I'll call x. We're going to times it by 23%, and it needs to give us the 5.28 kilograms of oxygen. So reverse percentage calculation here. And it will bump it up to be a bigger number, probably about 15, 20 maybe, because we're doing a bit of extra oxygen, aren't we? A bit of extra, 22.95. Normally it's about 15, 16. Normally it's about 17 to 1. Okay, 22.956. So x is equal to 22.956957 kilograms. I rounded that up. Let me just double check. Not that anyone really cares about the roundings on the end. 95s, yes it is. 22.95 kilograms of air is required. This is stoic air. Let's say that's stoic air. This amount of air you need to bring into the engine to burn that amount of fuel, assuming complete combustion takes place, which is probably not going to happen. So you need a bit of extra, but they don't talk about that. The mass of CO2, amount of carbon dioxide in the exhaust gases. Okay, carbon dioxide then, because we've done part A. I'm just going to separate out all the rest of it, because we don't need all this stuff getting close together. Okay, so the amount of CO2, so if you look at our combustion reaction, where does the CO2 come from? There's no CO2 in the air. We're assuming air is exactly 23% oxygen and 77% nitrogen, and there's no CO2 in that air. The real levels of CO2 in air are very, very small anyway. We can basically ignore them. So the only place CO2 comes from is here. It comes from our combustion reaction, right? We are going to be introducing CO2 because we're burning the carbon, not the hydrogen. This just makes water, which we don't care about. We do care about the CO2 being produced, and what we can do is say if we add together this mass plus this mass, we should get the mass of the CO2 produced, because we're using conservation of mass laws. The weight or the mass doesn't actually change of the inputs and the outputs. So that we should be able to say the mass of carbon plus the mass of the oxygen used to burn that carbon should equal the mass of the CO2 produced. Okay, that's actually very easy because we know the mass of the carbon. Aren't we burning 1.26 kilograms of carbon? Yes, I think we are. Here we go. And how much oxygen do we require to burn that? We said it was 3.36. So if you add these two together, we should get the mass of CO2 produced, and that's it. Very easy question because of how we did all the previous work. We did so much work earlier that listing all this out, like, you can just cherry pick what you need from it. So 4.62 kilograms. That would be the mass of CO2 produced in the exhaust gases. Luckily, they do not ask about the amount of percentage-wise, because it'll be a little bit harder to do that. It won't be too much harder. I mean, we know we're bringing in this amount of air. We're adding in 1.5 kilograms of fuel, so that comes out as in the exhaust, in the CO2, stuff like that. Some of this air will be transformed into, because we're taking the oxygen out of it and transformed into the CO2. But we could work out the total amount of air as well. But we don't need any of that. I'm just making up more problems. We don't need to make up problems. We've got enough as it is. Right. Okay, that was the end of number 5. Okay, we're going to do the next one, which is in part B, section B, which is a lot of electronics, basically. The first one was all pressure and gases and combustion questions, and diesel engine questions, Q-McT equations, stuff like that. Now, section B is all electronics. We've got a couple of electronic questions coming up. I haven't done this one for a while, so I might be a bit rusty at it. We'll give it a go. That was an easy one, a classic. And then that's an easy one as well. So there's no one more afterwards, but I don't think it'll be very difficult. Or the naval arc. Oh yes, naval arc at the end as well. And they're quite an easy naval arc questions, luckily. Okay, so these ones are a bit of a pain. And this is a bit of a special one because we're doing it backwards because they've given us the power, which is normally what we're calculating. We're normally calculating the power to start with. So the usual approach of this is going to be, well, maybe a little bit different to what we're used to. So we're using PIV and VIR, and they want to know the supply current. Well, I think we can just get that straight away using PIV. I should have called this VIP instead of PIV, but whatever. Power is 7,500 watts. The current, we don't know. That's what we're going to calculate. And the voltage, supply voltage, is 50 volts. I like how they're drawing a little arrow on there to show the direction that the electrons are not going in. I don't know why they did that. Why would, to show it's connected, maybe? I don't know. 50 volts across this section. I'm just joking. I like how they put little arrows here pointing inwards to show you the current is flowing towards the negative. It doesn't. That's conventional current, isn't it? Not electron flow. Okay, well, whatever. I'm just joking. Okay, let's get the 50 in there. This will be a calculation. 7500 divided by 50 will give us the X on that. Let's get the calculator out. Okay, let's get the calculator out, and we'll do 7500 divided by 50. 150 amps. Wow, that's a lot of amps. So 150 amps is going to be the X, which is our current. And that's the supply current. All right, well, then the current flowing through the R1 resistor. So I should probably draw a diagram and start using that. I didn't do that to start with. Should have kind of done it to start with, I suppose. Let's get a little diagram. So they got, this is the first thing I always do actually. I wonder if I can draw it up here. Two resistors in parallel with each other and being supplied from a 50 volt supply. Like this. Whoops. Alright, that will do. I can do it with not touching lines, but I can't do it with wonky lines apparently. This is 50 volts. This guy up here is 20 ohms. This one we don't know. And this is resistor 1. They've helpfully labeled it up for us as R1. I was going to do this anyway. I call this R1 and R2, or 1, 2, component 1, component 2, plus side of the battery or power supply, whatever. Okay, this is what we've got. Very nice. And if we know we got 150 amps going around the circuit, then we can work out how much goes through each of the resistors, especially if they gave us the resistance of the top one. We can work out how much current is going to go through there. So what's going to happen to the current is it's going to come up here 150 amps, and it's going to get to this junction. It's going to split, and some of the amps will go through the top one, some of the amps will go through the bottom one, and it will combine again to be the 150 amps coming back again. So let's find the current going through that top resistor. I'm going to annotate my work a little bit as we go. So this will be find the current in R1. Using Ohm's law, we should be able to use VIR in here to get it. So we've got VIR, because we know the supply voltage to this whole parallel section is 50 volts. So this guy's got 50 volts and 20 ohms, and we can work out the I. So I is V over R, and the total supply voltage is 50. The resistance is 20. That'll give us a 2.5, won't it? If I do it in my head, I could do it on the calculator, but I think it's going to be okay. 2.5 amps. Now if there's 2.5 amps, there's a little trickle going through this top bit, there must be the remaining amount going through the bottom. If it's 150 amps in total, the calculation will be 150 amps minus the 2.5, giving us 147.5 amps going through the bottom resistor. And that's the ampage going through R2. Let's just double check that all that on a calculator. I did it in my head. Of course it gets me 2.5, and 150 minus 2.5 is 147.5. Okay, so very large amps going through the bottom one, very small ampage going through the top one. This is a normal setup in a heavy piece of equipment where you want large amps to go through here, and a light amount of ampage to go through the top circuit. This top circuit will be the controlling circuit. It allows us to measure the amount of amps and also control the amount of amps in the total circuit. Okay, so a usual control circuit actually like this. Okay, the value, I'm just trying to work out if this is a shunt A shunt resistor, or what's the other one? A multiplier. Is it a multiplier resistor? Oh my goodness. It's been such a long time. Yeah, shunt resistor. Yeah, or multiplier. Okay. It's working as a shunt, isn't it? Is it? Oh, I shouldn't say things like that unless I know for sure. Never mind. We've got enough problems. This is it. We get it. We did it. The current flowing through R1. What? The current flowing through R1? Okay, I went overboard here. I went too far. The current flowing through R1 is just this much. We didn't need this extra information. I didn't read it carefully. This is the current going through R1. Now for part C, the value of R2, if we know the amps and then we also know the supply voltage, we can get the R from it using VIR. So I was a bit over the top there, but caught it. So we know this is the supply ampage. We've also got 50 volts being supplied to it. So using VIR again, I'll tell you what, let's make it just like a different color, just so it looks different. And this time we want to find the R, right? So R is going to be supply voltage over I. The supply voltage is 50 volts because it's in parallel. It's definitely be getting 50 volts. The amps going into it, we did calculate on the last one to be this. So it's going to be a very small resistance. So it is a shunt, isn't it? So 50 divided by 147.5. Okay, 0 0.3, 33.89.8. 33.89.8 ohms. That should be the resistance on R3. I meant R2 there. Very low resistance. Just check I got those numbers right. Yes, looks good. Alright, that is it. The energy consumed in the 20 ohm resistor in 5 minutes. That's a little bit strange as well. It's not the whole circuit, is it? It's just that little bit. I tell you what, let's grab this question. Let's move it all. Whoop. Let's grab this circuit as well, the circuit diagram, just so I can take a fresh look at it. The energy consumed in 5 minutes. So for part D, we can use power. Energy is. I think about this. We normally do power. I mean energy for electrical energy. Sorry, as kilowatt hours. Right, you measure kilowatt hours. That will be if you ran a electric kettle, which is 1,000 watts for 1 hour, it'd use 1 kilowatt hour. That's how you buy and sell energy of electricity. We don't do it in power, which is a bit strange. So this will be done in 1 kilowatt hour. It's kilowatt hours. Or is it per hour? Oh, it's been a while. Let me just check that real quick. Okay, yeah. I think I got the answers just up there. I did it the other day, well, months ago, when this paper first came out. And I was just checking my notes up here. I got my calculation up here. Kilowatts. Kilowatt hours is kilowatt hours, right? Yeah, because you'd be kilowatts times by the number of hours that you're using it for. Not divided by, not kilowatts per hour. Okay, so I had to mix that up. So the energy consumed by the 20 ohm resistor. So I'm going to use PIV to do this, to get the power, and we'll talk about it afterwards. Energy consumed by the 20 ohm resistor. We know the current going through this guy. We calculated it earlier. It was 2.5, wasn't it? I've got it written down somewhere, 2.5. The supply voltage is 50 volts. So 2.5 times by 50 should get us the wattage of this guy. So 2.5 times by 50 is 125 watts. 125 watts. Now, watt is a joule per second. 125 joules per second. And we're going to run this for 5 minutes. So if we times that by 60, that would be 1 minute. And that will actually cancel out this 60 seconds. And then times it by 5 to get the 5 minutes out of it. Then it will come out to be energy as just joules. So 125 times by 60 times by 5, because we're running it for 5 minutes. So 125 is per second, times by 60, that's now per minute, times by 5, that's now 5 minutes. 37,000. 37500. And this is done in joules. And it's actually okay to leave it that way because this is pure energy, it's the energy. It's not how we normally talk about electrical energy. We normally talk about electrical energy in terms of kilowatt hours, as I was trying to work out earlier. To get this into kilowatt hours, what we're going to do to it is a watt is a joule per second again, isn't it? So I could do it from this calculation here. If I This is fine. I should be able to leave it like joules. But you can see this 125 watts. That would be the same as 0.125 kilowatts. And we would normally measure this in kilowatt hours, but we're only going to use it for 5 minutes. So this is in kilowatts. And then we'd normally, if you just ran that for 1 hour, it would be 0.125 kilowatt hours. But we're not running it for an hour. We're running it for 5 out of 60th of an hour because we're only running it for 5 minutes. So I don't like this version as much. It depends. Normally we're running it for like 24 hours and we would give the answer in kilowatt hours, and we're running much larger amounts, but this is tiny. 5 divided by 60 is actually 1/12. We're running it for 1/12 of an hour, and we could times that by 0.125. So we get this as our answer, which I don't like so much. 0.0104 166, and this is kilowatt hours. That's normally how you'd measure energy for electricity, and this is normally energy, mechanical energy, but it's the same thing. They're exactly the same. This will actually convert into that many joules, and this many joules will convert into this many kilowatt hours. You probably times it by 3.6 or 3,600 to get it in there somewhere. There'll be seconds to hours and kilo in there as well. Yeah, I'm not going to do it, but yeah, actually you can see if you times it up by, I bet you just times that by just really big numbers like 3,600. I bet you times it by, I shouldn't do this, 360. This is to get seconds into hours, and then to get into kilo, you times it up, and you get the same number of joules. So they're convertible. They're essentially just like different ways. It's like saying it in miles per hour and kilometers per hour. It's the same thing at the end of the day. It just looks different sets of units. I would really stick to the joules on it, on this case, because we just use the PIV calculation, and it's pretty straightforward to get in joules. Joules is energy. Kilowatt hours, like I said, is a special case usually for electrical energy, but it depends on what we're talking about. So that's the end of number 7. A bit of a clunky one. I mean, normally these March papers are really hard. It hasn't been too bad just yet. It's been pretty standard, actually. Okay, let's look at the next one, number 8. Define resistivity of material. Resistivity, not resistance, resistivity is like a characteristic of the material. It's like, I would say, intrinsic resistance of the material. And how you measure it, how you make it, is you take a cubic meter of the material and you measure the resistance across it. And that actually gives you its resistivity. I'm trying to make this into a clear block. Whoops. Let's get rid of all these. This is actually like the definition given is you take a cubic meter of your material, which is a bit big. You know, you wouldn't really have a cubic meter of gold lying around to really measure it, but you can scale it down. Resistivity, now the formula will be resistance, should be resistivity, what is it? I'm going to get this mixed up. Times by the length divided by area? Oh, it's been such a long time I haven't done this. Because like if you had a longer length, then that would increase its resistance, right? If you had like a kilometer or 2 kilometers, the longer it is. And then the area, if the bigger the area, the less resistance you can have, because the thicker the material, the better, right? The less resistance. So I think it's definitely this way around. I think it's definitely this. Okay, resistance is going to be these guys. That'll be its formula. And let's give it a one-line definition to say resistivity is the, I don't want to say intrinsic because it's a bit of a nothing word, is the internal, I don't want to say internal resistance either because that's another thing, intrinsic resistance of a material. That's as good as I can get. And it's measured in ohm meters. The units are ohm meters, and intrinsic, yes, okay, great, I spelled it correctly. This is a material. Another way to say it would be the complete opposite of the conductivity of a material. You can't really measure the conductivity, electrical conductivity, so we measure its resistivity, and they'll be complete opposites of each other. The higher the resistance, the lower the conductivity, and the higher the conductivity, the lower the resistance. The intrinsic resistance of material measured in ohm meters. As units of this, and this is a formula for determining it. I could actually explain the formula if I want to expand this out a little bit more. I could say a bit more about it. It's just really seeing the difference between resistivity and total resistance, where resistance is measured in ohms. And I could transpose this formula to say the resistance times by the area divided by the length would give you the resistivity there, written as rho. I should really explain this formula because it's just symbols and nobody knows what these symbols mean. So this would be the resistance measured in ohms of the material. What you do is you take a kilometer of cable and you can measure its resistance, times by the cross-sectional area, that would be done in meters squared, divided by the length of the conductor, the length in meters. And this will give you rho, which is ohm meters, and this is its resistivity. Well, that's quite a full definition now. Okay. I haven't done this question for a few years now, actually, because I took it out of the training material because I just haven't seen it come up because it's such a crummy question. The way it's put together is just so bad. Let's just make a bit more space. So we're going to do it. It's a classic. Okay. The resistance of 1.9 kilometers of copper wire with a diameter of this much, okay, it has this many ohms. Determine the resistance of 1 kilometer of iron wire. So we're going to start off with copper, and then we're going to move this into iron, knowing this vague, roundabout, relationship between iron and copper. There's so many problems with this question, and we're going to use the formula of resistance is rho times by the length divided by the area. Hopefully that's right, otherwise I have to redo this section. That looks all right to me, doesn't it? I just justified it. So, should be fine. R, rho, L, and A. Do we know the resistance of the copper? Yeah, it's given as 170 ohms. Do we know the resistivity? No, we don't. We're actually going to calculate that. Once we get that resistivity, we're going to times it by 5.9 to get the resistance of iron, the resistivity of iron, well, approximately, which is crazy. That's the crazy thing about it. Is like, why are you using pure copper to approximate pure iron? Like, we don't know if these materials are pure, so we shouldn't even do this. Really, it's really, really bad. Okay, so the length of the copper is given as 1,900 meters, and the cross-sectional area, we're going to convert this millimeters down into cross-sectional area in meters because we're working ohm meters on the rho, on the resistivity. So this should be done in meters, and I'm going to use that little trick earlier that we saw earlier of 0.5 divided by 2,000 pi r squared. So that turns it into the radius in meters and then times it by pi. And it's just to avoid having a second calculation off to the side to make it even more cluttered. So let's do this calculation. 0.5. If you divide it by, I'm going to do it manually, basically divide it by 2, that gives me my radius, divided by 1,000, that gets into meters, and squaring it, and then timesing it by pi, you get this cross-sectional area in meters, which is very, very small. 1.9634 times by 10 to the negative 7, I think it was. Let's bring it back up again. Yeah. 96.349, 96.34, and then some other stuff. I think that'll be fine. This is meters squared. All right, okay. And now we can use this to work out the rho. So I transposed the formula a second ago. I said if you take the rho, the resistance, times it by the area and divide it by the length, you should get the rho. You could put the numbers in and rearrange them, but as I just did it earlier, I'll just pop it all down like that. Here's the area. And there's the resistance, and we times that or divide it by the length of the 1,900. So I've already got this number in my calculator, times it by 170, and then divide it by 1,900, and we get the answer of 1.75. And this is the resistivity of copper. 17568, one of the most conductive materials known. Times by, let's write down maybe a couple more digits on that. What is it? 8119, 8116 times by 10 to the negative 8, I think it is. Yeah, negative 8. And this is ohm meters. This is just like known. If you Google, look it up, we'll find the actual like pure copper will probably be a little bit smaller than this. This is probably not so pure. Okay, pretty pure, but like, 99% pure. Don't know. Not sure, but negative 8 is definitely the right kind of number for copper resistivity. Now we're going to times it by 5.9, which is such a rough approximation. It's insane. because we're taking so many things into account here, just ignoring so many things, I should say. Like what about the purity of these two materials? We don't know. So I times it by my resistivity there by 5.9 to get 1.0365 times by 10 to the negative 7 ohm meters. All right, so that's what we had to do in order to get into this approximation of iron. I'm going to look that up. Pure iron would not be brittle. Carbon, cast iron would be. But pure iron, pure material would not be brittle, it would be soft. So it would be malleable. Don't know how conductive it is. Well, that's the conductivity. It's actually 6 times more resistant than copper, which is not great. Okay. Now, what are we going to do? We've got the resistance of 1 kilometer. So the length will be 1,000 meters. And the area is 1 millimeter diameter. So 1 divided by 2,000 squared times by pi. We're going to calculate this out as a separate number. And then we're going to just put it all together. And because we're going to calculate that out as a separate number, I'm going to write down a few extra digits here on this one, because I want it to be quite accurate as I can make it. So 356,18892. This is as good as I can get, or need to get, really. Okay, let's calculate this guy, because we're going to take that 1 millimeter. We're going to divide it by 2 to get the radius. We're going to divide it by 1,000 to get it into the radius in meters, and then we're going to square it and times it by pi. Usual setup, you do this quite a lot, so okay. So the area there is 7.85398 times by 10 to the negative 7 meters squared. Hopefully that's okay. And the final calculation will be the resistance, because that's what we're going to calculate, the resistance of this iron wire. Resistance is equal to rho L over A, and the rho is this number. The L is 1,000, and the area is actually this number as well. That's interesting, because I can see the 10 to the negative 7s actually just cancel out completely. I'm still going to type this into my calculator, because I will, but I could just simplify on the page. It's just a little bit sketchy to simplify stuff, because you might make a mistake. So I do it both ways, really, to double check. Here we go, times by 10 to the negative 7. I can kind of eyeball the answers, what I'm trying to say with all that. I can check. It's going to be, these are going to cancel out. It would be like 1 times by 1,000 divided by 7. So whatever 1,000 divided by 10 would be about 100. So it's going to come out to be 120, I reckon, because they always come out to be the same answer. 785,398 times by 10 to the power of negative 7. 131.97. 131.97 ohms should be the resistance of that kilometer of iron wire, and that would be the final answer here. So resistance of iron wire is this one. I've got quite a few boxes on here, and the only thing I can say to check this answer is that it should be about the same resistance that you started with, within the same kind of ballpark figure. It shouldn't be 1 ohm or 1,000 ohms. If this is 170, then the other one would be about the same, or within the same kind of magnitude, the same kind of size, like not massively different. Such a weird question. They've taken it out. It's the first time I've seen it in about 3 years or something. And again, it's probably because of the changing of the offices that they just put it back in there. Okay, let's do another one. That was number 8. Let's check out number 9. Oh, an electric fire. Electric fire is operated electric heater from a 230 volt power supply heating element comprising of 2 25 ohm coils. The coils may be connected in series to give a low setting or in parallel to give a high setting. This is the classic question. It's so easy. I'm going to speed through it quite quickly because I'm sure you've seen it a lot of times before and there's really no problem with it. We're going to do this as a setup. The first one is going to be 2 heating elements. Oh, I actually draw them as heating elements. I apologize. I'm just going to draw them as resistors. Here's the heating element with 25 ohms, and the first one we're going to set them up in series. So here's the low setting. Let's hook these guys up in series. We'll hook it up to a power supply as well, and the power supply is 230 volts power supply, and this is for part A. This is in series for the low setting. For part B, we will set them up in parallel. So let's do that while we're here. You can draw it on later, so you got space on your page to get it on. There we go. Okay. Okay. And same thing, 230 volt power supply. Very nice. All right, and that's going to be for part B. And the first thing we want to do is combine these two resistors together. These are going to be considered to be resistors into a single resistor, so we can work out the amps flowing through the circuit, of course, right? So we can do resistors in series. In series, the formula for resistance in series is RT is just R1 plus R2. We just add them together. So the resistance total will be 25 plus 25. This gives me 50 ohms. So the total resistance of the whole circuit is 50 ohms. This takes us down to the circuit information where we can calculate the ampage. So you've got VIR, supply voltage is 230 volts. The total resistance of the whole circuit is 50. And then using VIR, we can calculate our current. It will be V over R, so that will be the 230 over the 50. So let's see what we get here. 230 divided by 50 gives me 4.6 exactly. So we've got 4.6 amps flowing through the circuit on its low setting. Let's just push this guy down over here somewhere. So this will be 4.6 amps. Wonderful. Now the question doesn't ask for that, it asks for power. Another power question. Don't we just do a power question back here? Power. Yeah, as we'll talk about, it started off with power as well. As I'm saying, they do double up on the questions quite a lot. So then we've got power calculation. So for power, we're going to use PIV. This is P is equal to IV. We can just consider the circuit as a whole. We do not need to break it down into individual elements, just the whole thing. So the power, the current flowing through the whole circuit is 4.6. The voltage being supplied was 230. So we just multiply these guys together and we see how much power it takes. So 4.6 times by 230 gives me 1058. 1058 watts will be consumed on its lower setting. That's for part A. We could write it as 1.058 kilowatts if you like. It doesn't ask for that in the question. We can just leave it as watts. The power output on the high setting. So we're going to do exactly the same process. Of course, this time it will be resistors in parallel. And that's going to give, too many R's in my parallel, yeah. That's going to give a much higher ampage rating, right? Because resistance in parallel, the form is 1 over RT is 1 over R1 plus 1 over R2. If these are 25, it's going to be 12.5, but we'll do the process. So it should be 1 over 25 plus 1 over 25. We're going to add them together and we're going to flip it, right? So 1 divided by 25 plus 1 divided by 25, 2 over 25, and then we do 1 divided by the answer in order to flip it to get our answer out of it, because there are totals on the bottom. So that's 12.5. So the total resistance of the circuit is 12.5 ohms, which is nice. It's wonderful. Now we can work out the ampage flowing through the circuit. So let's work out the circuit information, which is usually to find out the missing components. And I'll just reiterate what we have here, right back down what we have. We've got the total resistance as being 12.5 ohms. The total voltage supplied is 230 volts, and we're going to work out the I using Ohm's law of VIR. So I is equal to V over R. So this is 230. Oh, let's write it so we can read it. 12.5, and we're going to be a much bigger ampage. I think it's going to be 4 times as big. 230 divided by 12.5 is because last time we literally halved it. Now we're literally doubling it, and that ends up being 4. So 18.4 amps. 18.4 amps going through the circuit. There we go. That's the ampage. All right, we're going to use that ampage to calculate the power consumption, because the question asks for power up here, doesn't it? It says calculate the power output. We do the power output of the whole circuit, including the cables and everything. We don't care about those cables really. So power is P is equal to IV. What I'm trying to say is you don't have to break it down into individual components like we do on some questions. So the current is 18.4. The voltage supplied was 230. So multiply these together. So take my number times by 230. We get 4232. 4232 watts. That's the power consumption on the highest setting, 4.2 kilowatts. Big powerful heater there. But usual standard question, very simple, very easy, very nice. Okay, we're going to do the next one in the series. This is, we just did number 9, and we're going to do number 10. This is number 10, and pretty easy I think, actually all of these. A conductor, 7.5 diameter, has an effective length and carrying a current. magnetic field, a force in conductor is 20 newtons. Flux density, magnetic flux, very straightforward. This will be F is equal to BIL sine theta, F bil sine theta, or FBI L sine theta. And the other one will be our B is equal to phi over A. I could just change this into AB is equal to phi. It'll be a lot easier to use, but okay. That's it as our usual setup. Let's just see if we've got the F, the B, the I, the L. The sine theta we can ignore because it's always at 90 degrees. It says it here, right angles, so we can ignore it. Again, simple situation really. They gave us the force, I think, yeah, 20 newtons generated. The flux density is this B, that will be done in Tesla. The current is at 20 amps given in the question, and the effective length is 400 millimeters, so that's 0.4 meters. There are actually a few different versions of this question, or like, similar ones using completely different formulas, but this is the one that comes up all the time. Okay, I think we can just plug these numbers in. So we got 20 is equal to x, 20 times by 0.4. Okay, I'll just get my calculator. Okay, we just get the calculator. Here we go. And we're just going to pop these guys in. I guess I'll do the right hand side there. 20 times by 0.4. It's 8. So 20 is equal to 8x. Oh, let's write this nice and clearly. Can't reread it. There we go. 20 times by 0.4, let's just double check that. Yep, it's 8. So of course we divide the 20 by 8. So 20 divided by 8 should equal our x, which is the number of Tesla in that question, which will be the flux density. So 20 divided by 8. That's a lot of 20s, isn't it? We could just cancel it out. We could do 1 divided by whatever. 2.5, and that should be our answer. This will be a 2.5, I apologize. There it is. 2.5 Tesla. And it's about what we're looking for. Normally the questions are about 1 to 2 to 3 Tesla, 1.4 or something like that. So 2.5 Tesla is really good. Okay, I think an MRI scanner is about 2 Tesla or 1.5 Tesla, so it's about that. That's pretty strong. But it's a very small, tiny little solenoid. This is literally the fuel injector. It's a fuel injector calculation, right? This one here. These are fuel injector calculations. And part B is going to be magnetic flux. And we've got the flux density up here, which is the B. The phi is what we're looking for. That will be done in Webers, WBs, right? The area is the size of the conductor. So we've got the B is 2.5 Tesla. Now the area is getting up here. We've got the diameter, the conductor diameter. We assume that we're talking about a little coil because that's how it is on fuel injectors, probably, right? On a solenoid. 7.5 millimeter diameter. We can use pi r squared. So, but again, it's in millimeters. We divide it by 2 to turn it into a radius. Divide it by 1,000 to get it into meters, and square it and times it by pi. Again, use that little trick just because it saves me having to do a little side calculation. So let's do it. 7.5 divided by 2. This will now be millimeters as the radius. Divide by 1,000, and then square it and then times it by pi. I did the same thing on the calculator as I did here. I just did it slower on the calculator. And I can do it again quickly just to check I haven't made any mistakes. But I think this looks right. 4.41786 times by 10 to the negative 5. This will be meters squared. That'll be the area of our conductor is literally a little area across here. And this has like implications and stuff like radio technology actually, but we're not going to talk about that. We're just doing solenoids for the course. Okay, so that's the area. We've got the area, we've got the Tesla. You can see we're going to multiply the A up with the B. So the calculation will be really A times by B is equal to our phi, which is what we're looking for. So this is the A, this was the B, and we can multiply those two numbers together, and we should get phi coming out of it. We've already got this number in the calculator, which is nice. There he is. And we get times this by 2.5. 1.104. 1.1044 times by 10 to the negative 4. I think that was. Let me just double check this. Okay, I got this as 1.10446644466. Suppose I should put another couple of digits on here. I don't really mind. It has to be like about 5 sig fig. Yeah, that looks good. And times by 10 to the negative 4, and this will be done in Webers. This will be the field strength. Is it field strength? What did it say here? Magnetic flux, which is, well, they're both field strengths, aren't they? Magnetic flux is how much magnetism there is passing through that little coil, is what it is. Is it measured in Webers? And we got it. Pretty straightforward. Nothing too difficult there. It's always about the same. 10 to the negative 4 for the Webers, and 2.5 for the Tesla as well. That was question number 10. Let's do the next one. So question number 11. Okay, naval architecture then, a little bit different. We did loads of electricity, now we're on naval arc. A ship has a displacement of this many tons. Determine the distance. A mass of 71 tons already on board must be moved off the center line to cause the ship to heel by exactly 1 degree. This is an old question. It was the same old numbers. They have not changed anything. They just put it in here. They even gave us the formula. The formula is md is equal to delta gm tan theta. There we go. And we just need the bits to put them all in and calculate it. We don't really even understand what's going on. Of course, we do understand what's going on. This is to do with moments. This is twisting moments or turning moments. Force times by distance, and this will be force times by distance. So m is the mass of the load, which we know is 71 tons. The distance is what we have to determine, so we set it equal to x. The delta is the displacement of the ship while loaded and is already on board, so we can count that as the 35,000 tons. 35,500 tons. Gm is the distance between the km and the kg. Let's use the big number minus the small number, but km minus kg, if you cancel out the k's, you get the m to g distance. That would be 6.2 minus 5.3, but I am just using big number minus small number to work it out, really. And I can rebuild it, you know, from my good boat if I really have to, from the cross-sectional diagram of a ship if I need to. 6.2 minus 5.3 gets me 0.9. There we go, 0.9 meters. So we got the GM, and the tan theta is going to be tan of 1 degree, which we can just plug in as is. We don't have to calculate it here. It's going to give us some horrible number. I'll just do it in the calculation. So we just put it all together and we're done for 8 marks. Oh my goodness. So there'll be 71x. 71 times by x is equal to 35500 times by the 0.9 times by the tan of 1 degree. And the only thing I'm going to do is divide down by 71 once I get this whole right-hand side. Let's get the whole right-hand side. Let's get it done first. So here it is. We're going to go 35500 times by 0.9 times by tan of 1. You don't even have to close up the brackets. It should be fine. Just check your calculus in degrees, not in radians. Otherwise you get some screwy answer. We got 577.68. 557.689. I might have said it a little bit differently there. Sorry about that. 557.689. Yes, okay, right. And this is equal to 71x, and then we divide this all by 71 to get a single x. So divide the answer by 71, 7.85. 7.845, I think. I keep reading the numbers wrong, so about that. Oh no, it is 54. 547, so I think it was an 8 after that. This is the distance that it has to be moved off the center line in order to cause the ship to heel by 1 degree. They're still using heel. List or heel. These guys. What is the difference between list and heel? And they chose the wrong one, right? Because heel is caused by external forces and list is internal forces. They did correct this on a very recent paper, but they just don't seem to get it right each time. Okay, so that was number 11. Very nice. Okay, so last question then. I was just looking up on Google the difference between list and heel, and yeah, they always get it wrong. Anyway, it doesn't matter. It doesn't make any difference to the question. Okay, so part 12 is determine the thrust load of a cofferdam bulkhead, 25 meters wide, 26. Oh, it's so classic. They're using the same old questions. This flooded with seawater on one side. So thrust load, we got 2 different calculations. I can draw a little diagram for what it's worth. It's not going to be very exciting. It'll be 25 meters wide, 26 meters deep. Oh, I do need a little calculation, don't I? Thrust loads, that's force, and this will be what? Rho g area affected h hat, I think. And the other one, gauge pressure at the bottom, we'll do that in a second. Oh, pressure will just be P is equal to rho g and then H, yes. So it's just been like a while since I've done these, like months and months. And because of the way we remember them, like you can actually study for the courses a long time before you actually take the exam, and you remember it all quite well. Like it all comes back quite quickly and quite easily. It's not like you do in school where you learn stuff and then you forget it all. Very quickly. Like that's the difference between my courses and school in general, is that I'm not using traditional school techniques. because you don't remember them very well, right? I've been teaching for a long time, and I've got my own little techniques that we've built up over the years, or taken from better places, I think, and they work very well. All right. Okay. So determine the thrust load. Let's see what we've got here. We're actually calculating F. I think that would be the force. The rho will be the density of the water, which is given as 1025 kilograms per cubic meter. The density, yes. Gravity, we assume we're on planet Earth, so 9.81 meters per second squared, technically. Don't even need these units, to be honest. The area being affected will be the 25 times by the 26, which is going to be a big number. We can calculate that right now. 25 times 26, 650. All right, and then the H hat is halfway down one of the sides, like it's like in the middle, isn't it? Because we're completely flooding this thing to the very top. Um, Probably says that somewhere when flooded. And so zero pressure at the top, and then the pressure would increase as we go down. If I draw like a little pressure profile, and we're taking the middle point, which is mathematically valid to do that, that's going to be 13 meters down. We just pop it all together. That's what I'm saying. Easy questions, straightforward. So x is equal to, or f is equal to the 1025, just make these look like actual numbers, that looks a bit weird, doesn't it? Times by 9.81, I prefer to use brackets, times by 650, times by 13. Whoa, very straightforward, just pop them all in. So 1025 times by 650 times by 9.81 times by 13. Sorry about that, slightly different order. Massive number, 84966. Okay, I can't remember all that. It's 84966,862.5 newtons. And they just said determine the thrust load, in meganewtons. Very nice. So we're going to put it into meganewtons. Mega means million. So this would be 84.96. We're going to round that up to 7 meganewtons worth of force on here. But I can do that on my calculator by pressing the engineering button, which is nice. Got this number on my calculator as the answer. I just press the eng, and it pops it into the most convenient 10 to the 3, 10 to the 6, 10 to the 9, because we're working with kilo, mega, and giga, and other ones. Well, actually not on the course, just those 3 on the course, but the calculator can do more, of course. But it does it to the nearest 3. That's what the engineering button does, to avoid counting errors, right? And we got that number, which is nice. That is the thrust load acting on the bulkhead. That's for part A. Now the gauge pressure, so that's the hydrostatic pressure rather than the total pressure, including the atmosphere. And that will be the lowest point of the bulkhead, and that height will be the full 26 meters, as if you were floating on the bottom or lying on the bottom of the tank. You get the pressure would be equal to the density, which is 1025, gravity, which is 9.81, and then the height, we're going to go for the full 26 meters. You're going right down to the bottom of the tank down here. So you want the full head of water on top of you to get the most pressure. And it says in bar. Okay, so this is going to come out in pascals. 1025 times by 9.81 times by 26 gets us the answer as 261436. 261436.5. This will be in pascals, which is newtons per meter squared as a pressure. And to convert from pascals into bar, you divide by 100,000. So it'll be 2.614365, or I could round this up to 4 bar. I divide them by 100,000 there to get it into bar. Something else I wanted to say about that. Oh yeah, of course, the rule of thumb, which is every 10 meters you go down, like a diver's rule of thumb, right? Every 10 meters you go down, we expect 1 bar increase. So going 26 meters down, we expect 2.6 bar. And it's pretty good. There it is. So we can check that's right. This is the lowest point in gauge pressure. Yeah, that is the hydrostatic pressure, not the atmospheric pressure. And then given in bar, that's what they wanted. And we did both of them. And that's the end of the test. Very nice.